Next highlight talk by Martin Suda. Just a few words about Martin. We are also very happy to have him here. He's a senior researcher here in the building and the head of the automated reasoning group. He'll probably talk about it, but just say he's one of the developers of the automated theorem proof Vampire, which, if I understand correctly, is one of the leading systems in the world in this area. So it's an honor to have Martin here with us. Few words about him. Previously, he was a postdoc at the Faculty of Informatics of Vienna University of Technology. And before that, he was a research associate at the University of Manchester before coming here. And he did his PhD, I think it was jointly between Charles University and the Max Planck Institute for Computer Science in Saarbrücken. So again, we are very happy to have Martin to build his team here with us, and he will tell us a little bit more about what he is up to in his research. Martin, floor is yours.
Thank you. Thank you, Josef, for the very nice introduction. So the talk is called Powering Automated Theorem Proofs by Machine Learning. I might start by thanking Josef Urban for inviting me here to CIIRC after my postdoc ended in Vienna, and initiating me to this topic and also pushing me to submit the proposal that led to the project that I'm going to talk about. Right. So we are. What is automated theorem proving? It's one of the classical disciplines of symbolic artificial intelligence, going back to the beginning of the computers, to the 50s, basically. And so here the task is we use logic basically as the formal language, so that's why it's symbolic. We describe things in the world in some formal language that is logic for us, and the main driving thing in the algorithms is logical deduction, which is sound ways of deriving new facts from already established facts. And what is important in this area, what is the key here, is that at the end of the thing we should get a proof, which is some kind of artifact that presents a witness for why what the algorithm has derived is actually true. It can be inspected, it can be verified, and so on. And Josef already mentioned this in the morning talk. We are in some sense going towards fulfilling Leibniz's dream of this calculus ratiocinator, which was this idea of a really universal language and also some kind of unambiguous way of resolving disputes and even discovering new knowledge that would be fully mechanized, and so there will be no doubt that the results are correct in some sense. We have various applications of theorem proving. The most obvious ones is new discoveries in mathematics, because one could argue that logic is the language of mathematics, but among other very important ones are verification of hardware and software. Holger already mentioned in the morning that without proper verification, we wouldn't be, with our technology, computing technology, where we are now. And concerning verification of software, you could verify day-to-day software that we use, there used to be this blue screen of death in Windows. It doesn't appear so often anymore. But more contemporary applications of this are also the correctness of algorithms that come out of machine learning, right? For instance, if a neural network drives your car, you might want to have some guarantees. We've already had some references to this topic before. All smart contracts, blockchain, finance applications where there is a lot of money in this, and smart contracts are also interesting in the sense that as a piece of software they are not so complex, so they are more easily attackable by these tools than some other things. And we are already starting some collaboration with an industrial partner on this. There is cryptography and security. You could verify cryptographic protocols. In natural language processing, there could be some semantic disambiguations of parsing of natural language and so on. So there is a challenge in this area, and there is also an opportunity. The main challenge is that Well, first, the technology is based on search, heuristic search. So in some sense, we don't have a better way how to do reasoning than by going through all the possibilities, and there are really many. So fundamental part of this topic is to do the heuristic research in a smart way. And what we are fighting against is the computational complexity. The more expressive your language, the more expressive the logic is, the harder is to do the reasoning. At least in the theory of algorithms, we have some explicit bounds, and in some more expressive logics like first-order logic that are becoming interesting for representing math, for instance, we know that the task is actually undecidable, so there is no algorithm that would succeed on all the inputs in finite time. But still, like, we know that humans do reason quite successfully, so there is a big motivation for us to try to imitate that. And the practical manifestation of computational complexity here is what we call combinatorial explosion. So when you try to combine things in all the possible ways, such that you don't miss some argument or some derivation, there is so many possibilities that you might get overwhelmed. And this is where the opportunity comes, and that's to use machine learning to derive from experience some new smarter heuristics, and also to possibly like make the prover adapt to application domains from the learning. And this was the topic of my project called Power.ai TP. Yes, so I wanted to talk a little bit about our workhorse, which is the automatic theorem prover called Vampire, which is a theorem prover for first-order logic, and it goes beyond that. So there is support for arithmetic reasoning and some other finesses. I'll give you a little bit details. I'll not to overwhelm you, but maybe take this opportunity to still teach you a little bit about theorem proving. So Vampire is something what we call refutational. So it relies on the method of proof by contradiction, which means that, so if you want to prove that some claim follows from your axioms, you negate that claim, and you try to derive absurdum by logical steps. It is saturation-based. I will explain in one slide what saturation is. And it's superposition-based. Superposition is this advanced logical calculus, so the precise rules how to derive new facts from the known ones, which has a built-in support for equality, and it's very important for math and also for other applications to be able to efficiently reason about which things are equal and which things are not. And we like to compete, and Vampire regularly enters several competitions, one of which the most famous is the CAS competition, and has collected throughout the years various trophies. And so I'm one of the developers, and this is the joint effort together with teams from Manchester and Vienna. Okay, saturation-based theorem proving in one slide. I promised I will not do too much of the details, but so there is some workflow, information flow in this picture happening from the input that needs to be processed, and there is some kind of pre-processing. And the unit of information, I might use this word in the few slides that come, the unit of information which we work with, it's a logical formula of some particular form. We call them clauses, and these are the blue dots that go from this container that is called passive, and they enter the container which is called active. 2 slides ago, I was mentioning the concept of combinatorial explosion, and this is where it happens in practice. In this hexagonal active set, you can think of it as a nuclear reactor, because whenever a single clause enters here, the task of the algorithm to achieve saturation in the limit is to consider all the possible interaction between the already activated clauses and this selected clause, and create logical consequences with respect to this logical calculus that we have here in the little cloud, which is the superposition inference rules. And everything that's created this way, the children of these interactions, are put back into passive. And you have this infinite cycle, and it terminates when you derive the obvious contradiction in the form of a specific clause, which is the empty clause, and that testifies the contradiction. Or or yeah, you run forever. For instance, if the conjecture actually doesn't follow from your axioms, that can happen in practice. And so this clause selection moment is when you take the next passive clause and activate it, is the most important heuristic choice point inside of a saturation-based prover. And so there is some kind of rough estimate about that the passive set is typically so much larger than the active set, and the proof, if we discover it, when we discover it, is much smaller than the active set. And implicitly, what should be clear now is that all the clauses that comprise the final proof must have been activated in some moment. And so if I'm saying that the typical proof is much smaller than the active set, it means that we are wasting a lot of effort because we are not able to navigate to the proof very efficiently. So this is where the opportunity for learning is the most stark one. And we have been mostly focusing on that clause selection choice point. And the core idea is what I would call learning from successes, and has been formulated some time ago. Actually, I think this reference, although it's incomplete, to Stefan Schulz's work goes even into the 90s. I think 96 from his his master thesis. And so the idea is to basically look at successful runs on the prover from the past and try to change the clause selection heuristic such that it promotes clauses that look like the ones from the proofs. And then Josef was already mentioning this first modern successful incarnation of this idea in the system Enigma. And there are some technicalities that need to be overcome. With any application of machine learning, we need to create our examples, which is quite easy. We just take the selected clauses from the past successful runs. But here, the challenge comes from how do we represent the symbolic objects that the clauses are the formulas. They are basically some kind of trees, and that doesn't fit very well with the modern algorithms of machine learning, which like vectors of real numbers. So there is some challenge in representing clauses as features, and we can use neural networks for that, or we can do handcrafted features, but different approaches would differ on this. And then once you get the trained model, there is this task of somehow integrating it back into the saturation loop, but I will not go onto details onto that. I will briefly mention, however, what I did, what we did in this project, where we added neural networks to power this important heuristic in Vampire by a particular incarnation where we used recursive neural networks, and they were trained to distinguish clauses based on their derivation history. So let's not discuss what derivation history is precisely, but I'll tell you what it isn't. The surprising result of this project was that you don't have to read at what the logical formulas, the clauses, what they are saying. You would probably want that in your ultimate system, because you would want your ultimate system to understand what the formulas are talking about. But you can achieve very good results by already just looking at the pedigree about what was combined with what. Maybe some axioms are really very explosive and they don't bring too much value, and so on. So basically, the network was able to capitalize on such hints. And the other upside was that this can be implemented very efficiently. Unlike reading larger and larger formulas and analyzing them with larger and larger networks, this can be done much efficiently. I will not ask you to understand this whole table. There's just two little pieces, little lessons to learn. One of them is, so in these columns, I can do the pointing. There are 3 versions of a model of a neural network that are trained on the data that came out of initial run of Vampire that solves something like 20,000 problems out of 50,000. That was my benchmark set. And just to confirm some common knowledge, the larger your network, the more accurate it becomes. But because we are doing good theorem proving, well, the algorithms are already very, very well optimized. Being precise is not the only only metric that we need to care about, because as you see in the actual performance, the middle model was the most successful one, and that's because the much larger, the twice as large model was too slow to evaluate. So there is a trade-off between how accurate the heuristic that you learn is and how efficient is to evaluate it. So that's the lesson. I think I will need to go through this a little bit faster. This is a second topic, something that we came across. In some sense, it is quite well known already in the field that these algorithms sometimes behave very weirdly, in the sense that you change just a little bit the formulation of your problem, and suddenly from something that's trivial and solved very fast, it becomes impossible to solve in some reasonable amount of time. So it's quite the opposite of what you know from running algorithms on some easy tasks, like searching through a graph, shortest path. We have polynomial guarantees for these algorithms here, because we are dealing with undecidable problems. Things can go wrong for some weird reasons that one could describe as some kind of manifestation of chaos. And so what we did in this work was to, and the chaos is bad, because then when you implement a new technique and you introduce it into the solver, into the prover, what can happen that by this change, you solve new problems, but it's not clear whether it's because the technique is smart or because it just, like, butterfly affected the search in the right direction and shouldn't be taking credit for that. And so what is nowadays being possible through the fact that we have powerful servers is that we could randomize the runs, and so by injecting extra noise, one could suddenly again see, like, basically the chaos disappears, and you start seeing some distributions that could be analyzed with the tools of statistics, and some nice conclusions can be drawn. I have an example which you should only try to understand in an abstract sense. So there was a work by my colleagues from Manchester, Giles Rigger and Michael Rawson, about some way of organizing a theorem-proving heuristic, and they were tuning some parameter, changing some parameter and observing how the prover behavior differs. Here is some kind of sweet spot, it's the fastest, and then you see some kind of like a jagged curve. If you insert randomization, so you try to do things insignificantly differently from the perspective of the main design of the algorithm, and then you rerun this many times, so this is like thousands of runs in this picture, you start seeing some weird pattern that's, unlike this jagged thing, it's obviously continuous, but so some deeper analysis would be required to see what's really going on. But we see that through randomization we get back from something jagged, something gets again continuous and maybe more meaningful. Right, and then we used this idea to empower the prover by creating so-called schedules of proving strategies. Well, the prover can be tuned in many ways. We call the tuning, or like there are several options how to set it up. And a particular setting of these options is called a strategy. And it's well known that different strategies work well for different problems. And it's also, like, because of this chaos maybe, it's really hard to predict in advance which strategy will work well for what problem. And so this is already known. State-of-the-art provers use strategy scheduling, so they can run many strategies in sequence or in parallel. And that's how you solve many more problems. And last year, with my PhD student Filip Bartek, we created this new system called Snake, where we used the randomization mainly as the main trick to achieve extra robustness. And we entered the CAS competition from last year, 2012, in a demonstrating division, because we were relying still on Vampire, and we didn't want to compete against Vampire for the medals. But so you see that there's certain categories they are called divisions, I think, in the competition. The most important division is probably the plain first order theorem proving, where we managed to beat Vampire proper by solving 9 additional problems. in some of the divisions, we didn't succeed so well overall because there are some specialist provers. For instance, this unit equality division where the clauses are not so complex, but the reasoning needs to be very deep because it's equational reasoning. We could improve much more over Vampire, but then we didn't match the competition. But the results were still very encouraging, with which I would like to wrap up. So this was a very exciting project. I was happy to be exposed to these challenges. The message from what I was saying in the first half is that there is, with theorem proving, needs to be a balanced stroke between how clever your heuristic is and how efficient it is to evaluate it. So computational efficiency, very important. The second message was that randomization could be a way to fight chaotic behaviors and improve prover robustness. And there are some things that we are working on right now, and I would be happy to discuss maybe later, but I don't think I have time anymore. Thank you.
Thank you very much for the presentation. Any questions from the audience? I see two. I will start with Patrick. Patrick, please.
So, two naive questions. The first one is, in the same way, AlphaGo seems to have discovered new strategies. So, is it the case that the new ways to solve theorems, different from what the humans are doing or the mathematicians are doing, have been discovered this way, or not at all? I mean, you solve a theorem, right?
Yes.
Or some theorems, and is it sometimes in ways which are quite surprising to the mathematicians or to the humans?
So is the question whether the theorems that we newly solved are interesting to the mathematicians?
Not the question is, even for old ones, is it solved in a way which is different or surprising to the mathematicians?
Yes, so sometimes, when you solve a problem, a human would do a task in a different way than a machine. So is it that the machine is finding ways which would be similar to human mathematicians would solve it, or is it completely different?
Yes, this is a very interesting question. I think the answer is not so easy, mainly because the way these calculi work, the ones that we are using in the provers and that are specifically made for the automation, but not so much to be immediately explainable to the mathematicians. So we typically don't look at the proofs, at least, well, for the trivial ones we do because we are debugging our solvers and so on. But if you solve something non-trivial, it could be hundreds of lines, thousands of lines, and you simply don't have the time to try to understand the particular ways of reasoning that the algorithm went through. And they could be probably like convoluted. There is some trade-off between explainability and between efficiency of finding the proofs, which is a very interesting topic. But and yes, I think we need to work on this more if we are to convince the mathematicians to use our tools. But so far we are probably optimizing in the direction of having the largest success rate. And I think it's like a second stage where you would want to explain what the proofs really are to the mathematicians. And I agree that's also a very important aspect.
Interesting. And my second question is that you are bringing machine learning to a task which is highly symbolic, so logic reasoning. And does it open up ways to do the opposite, to help? I mean, in other fields like mine, it's mostly data-driven, and we are now dreaming of a nice way to bring back reasoning and symbolic into these very data-driven machineries. So does your research also hints towards a way to bring reasoning and symbolic reasoning to hardcore machine learning?
This is definitely happening. There are some results already. I wasn't focusing in my work on this, but there is definitely very, very much of interest in using these techniques to, for instance, verifying neural networks, and yeah, it's all being done. It's very exciting, and there's many more combinations that you could think of just to be discovered and to be researched on. So I think we are in the right place at the right time.
Excellent. That's a very nice final note. So thanks, Martin, very much.